So this video required symbolic derivation of the heights. We were able to find that in order to apply the heights to use to the test in order to see if our equations and calculations were true. So you start with the kinematics equation of delta y equals 1/2 at squared plus initial velocity times time. Since we have to understand that the initial velocity is 0 because the toilet paper started at rest, we're able to isolate the equation where we can find delta y equals 1/2 at squared. And by isolating t, we get the square root of 2 delta y over a. So the free-falling roll must maintain an acceleration of g over its own height, while the rolling roll has to maintain an acceleration of a over its height. Since the principle of this lab is for both rolls to take an equal time to touch the ground, we're able to find that we're going to use both t equations, where we find the radical of 2h1 over g is equal to the radical of 2h2 over a. And after isolating both of the h's, we're able to find that h1 over h2 is equal to g over a. So we then apply the rotational inertia of the cylinder, which was given by 1/2 m open bracket r inner radius squared plus r outer radius squared. But since the axis of rotation was not in the center of the mass, we applied the parallel axis theorem, which provided another mr outer radius squared to our equation. This allowed us to find the equation of 1/2 m open bracket r inner radius squared plus r outer radius squared close bracket plus mr squared of the outer radius, which then simplified leads to 1/2 m times open bracket r squared inner radius plus 3 outer radius squared close bracket. So we implemented the torque formula where we found the angular acceleration times the inertia is equivalent to the force times the radius, and with that we found that the angular acceleration times the radius is equivalent to a, so we solved for a as a result. And since we already knew that the force times the outer radius was equal to the inertia times the angular acceleration, we were able to isolate the formula where we found the acceleration is equal to mg r squared outer radius over 1/2 m times open bracket r squared of the inner radius plus 3r squared of the outer radius close bracket. So since we already knew that h1 over h2 equals g over a, we applied the a that we just found using our radiuses of 2.3 centimeters and 6.9 centimeters, and we found a ratio of 1.55, repeating. So after doing the drop, we measured the length that it took for us to drop each of the toilet papers using yarn, since we did not have meter sticks at home. Eventually, we were able to find a sweet spot where both of the rolls dropped at the exact same time. So we were able to maintain that the height of the free-falling or unrolled toilet paper roll was 2.07 meters, while the other one that was rolling was 1.372 meters. We divided both of the heights together to find a ratio of 1.51, and this is very, very close to our original theoretical ratio of 1.55, and this difference can basically be attributed to error. Sources of error can include air resistance. Since this is not an ideal environment, there will be a drag force that's acting on both of the toilet paper rolls. Another source of error could be the way the toilet paper rolls are spinning as they fall. Other potential sources of error could include the fact that we assumed both masses to be the same, when in reality we do understand that the masses of both toilet paper are going to be different. Another error could come from a precision error, which is why we got 1.51 rather than 1.55. It could be dependent on the fact that we weren't as precise with our numbers, which led us to be slightly off in the final ratio.